The first time I went through it, I made a whole bunch of mistakes, and I was working with somebody who's now, well, he's a science educator. He's one of the smartest people I've ever met, and the two of us were both just like, and you'll see why momentarily. There's a lot of details that go into this. There's a lot of places where you could make either small mistakes or miss big insights. What I'm gonna try to clarify for you is which of these things you should already know, and maybe you still need to think about them, but there's the things that I think everybody's ready to really lock in. The things that are trickier, but I hope you get, and the things that lie in the realm of like, well, this is not reasonable to assume that you would have figured this out the first time around. Some of you might have, but most of you probably didn't for very understandable reasons, okay? So here's our setup. For those of you who don't remember, we have these concentric pulleys, and I'm gonna do a spoiler alert and say we're not actually gonna test our predictions. We're gonna make a prediction, we're not gonna test it. The reason is because testing the prediction with these things involves setting them up and winding the strings and hanging masses and making measurements, and you end up just spending like a lot of time winding strings. It ends up being this dexterity exercise that's just not worth it under the circumstances. Normally I would have you do it, but we're gonna plow ahead. This concentric pulley has 1, 2, 3, 4 radii, but we would only use these two inner ones. And one, I don't remember what they are, and it doesn't matter, because we're just gonna call the one that goes off to the left R1, that would be this one right here. And then the one that goes off to the right, we're gonna call R2, and that's this one right here. This, I have this one string untaped, so you can kind of see how motion about that pulley would look if I were pulling on the string. And then the setup continues that you would have a string wrapped around the inner pulley with a mass hanging off of it, and we'll say that that's M2, and then another string hanging off outer pulley, the mass hanging off of that, and we'll call that one M1. We don't know, given this diagram with no numbers, we can make no prediction about what would happen. Depending on the masses that we put on here, if it were motionless to start with, it might remain motionless. If we hung a really large mass here and a really small mass here, it would accelerate clockwise. And we know it would accelerate because there's no reason to think that any of the torques would change as it was moving. So if it starts to spin, it's just gonna spin faster and faster and faster. If we hung a really large mass off the left side, a real tiny mass off the right side, then it would accelerate in the counterclockwise direction. So we can't look at this and be like, well, it's always gonna move in this way or that way. We don't know. But the actual numbers that I gave you are designed to cause it to accelerate counterclockwise. And that is, I did that on purpose because that's our positive direction. And so we wouldn't have known this, but it makes it easier when you're testing your measurements, when you're testing your predictions, to have counterclockwise be positive and have that be the direction of the actual acceleration when it's all said and done. Okay, so this is the setup, and then the last thing that I told you is we know the moment of inertia of the concentric pulley. And in the last class, somebody asked me, wait, what's the mass of the pulley? But the mass of the pulley doesn't matter. Mass does not matter because it is not accelerating in a linear motion. It's not accelerating in a straight line. It's experiencing angular acceleration. It's rotating more and more quickly. What matters is the angular mass, and that's what I is. I determined this experimentally years ago, and it's really small, but non-zero.
So with the things given to us, mass is a non-factor, it would remain the same regardless of mass of the pulley?
No, that's such a great question though. That's not exactly right. It's just that where the mass is matters too. So knowing how much mass it has can't help you solve this problem. Knowing where mass is located, but not knowing how much there is, can't help you solve the problem. You need to know two things: how much mass and where is it located, and that's all summed up in this piece of information right here.
That's what inertia is?
That's what moment of inertia
Moment of
is.
inertia
Yeah,
is.
moment of inertia, variable I, tells us both how much mass something has and where that mass is located relative to the center of rotation. This right here is what I call angular mass, angular mass. And it's a weird one. Conceptually, this is weird because it's just like, well, wait a second, do we care about what does that really mean? And the answer is, think about the fact that if you make this thing more massive, it will be more difficult to accelerate it and more difficult to give it angular acceleration. But also, if you take its existing mass and move its existing mass away from the center, it becomes more difficult. You can't just use mass, just like with these plastic tubes, you can't just use mass. They have the exact same mass, but the red one has a much smaller moment of inertia because it's located right at the handle. So when I twist it like this, I can feel the difference. When I move it up and down like this, I can't. That's the difference between mass. Mass determines resistance to linear change in motion. Angular mass, or moment of inertia, determines resistance to twisting motion. And it's weird. The best way to nail it down is to play around with it, and we will a little bit, and we will more later this week. Okay, does that make at least a little bit of sense? Go ahead.
Yeah, I guess my question then is that, I might have missed this, but what is, if that's what moment of inertia equals, what is the formula for moment of inertia?
There is no formula.
There's no formula.
Yeah, so the thing about moment of inertia is, if we happen to know that an object has a regular, symmetrical shape, it's uniform in density, and we know where it's going to be spun, we know the axis of rotation, then people have figured out what the moment of inertia is in terms of the mass and in terms of the size of the object. So this, if you told me we're going to spin this around like this, I could tell you what its moment of inertia was simply by measuring length and width and height and measuring its mass. If you told me, wait, nope, we're going to spin it like this, I'd still be able to do the same thing. If we spun it like this, so that the axis of rotation was right here, I could still do it. We figured all that stuff out. But if we were to make the axis of rotation start here and kind of go through and come out here, so that, I can't do this because I don't have a drill, but if it were like this and it were spinning around like this, forget it. There is no equation for it. So we determine it experimentally. We apply a known torque, we measure the resulting angular acceleration, and divide those two things. That will tell us the moment of inertia. It's not the formula for moment of inertia. It is a way to experimentally determine moment of inertia. That's what I did with this. Because this, if I were to find the mass would include, most of the mass of this thing is in this bar, and that bar doesn't rotate. When this thing spins, the bar is motionless. So the bar doesn't contribute to moment of inertia at all because it's not spinning one little teeny tiny bit. What determines the moment of inertia of this thing is the mass of the part that is spinning, and I can't measure that without taking the bar out, which I'm not going to do. And even if I did, there's still parts in here that don't spin. Not only that, but this isn't a uniform shape. So measuring its mass and its size isn't going to give me something that I can plug into a formula and use to find moment of inertia. I found moment of inertia here by applying a known torque on one of these pulleys and then measuring the resulting angular acceleration. Then I could use Newton's second law and figure it out. All right, so let's cruise here. So all of this stuff was given. Here's where it starts to get interesting. Number one, I know that everybody here would be able to recognize that this mass on the left would be accelerating downward, and this mass on the right would be accelerating upward. But here's something interesting. They're not accelerating at the same rate. And this wouldn't necessarily be something that I would expect you to predict, but if you think about it, it makes sense. Why? Because this string is wrapping up as this mass accelerates upward. This string is unwinding as this mass accelerates downward. The outermost pulley has a larger radius. So for every rotation of our concentric pulley, the mass on the left will move farther. Mass on the right will move a smaller distance because the inner pulley has a smaller diameter. That means that they must be moving at different speeds, and they will therefore have different accelerations. So the downward acceleration of this is going to be greater than the upward acceleration of this. They do not have accelerations of the same magnitude. Okay, and you can make it ridiculous by imagining that this inner wheel is tiny, just this tiny little pulley, and like this mass is down here, and this one is huge, as big as the whole board. And you can imagine that as this one unwinds, it's going to fall fast, and as this one goes up, it's just going to like wind up really, 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 really slowly, which is exactly what would happen. All right, here's some more stuff to think about. When we look at where this string is, the way this drawing is made, it kind of looks like this thing would rotate like this. The way the drawing is made, if I were to pull on this string, it kind of looks like it would go like this, right? And then just pull straight down. So it's on the side right now, but when I pull, it drops and it becomes attached here, and it's just going to pull straight down. This one will pull straight down, this one will go up and then come back down and then pull straight down. But that's not what happens. What happens, because the string is wound up, is that as you pull it, it is always pulling from the same relative location. It's always pulling at a perfect 90-degree angle down. So this string, while it gets longer, doesn't change where it's pulling on the pulley. And that's important because it's the force from these two strings that really combine to create the overall torque on the pulley. There's a force from this string downward. That force we can call T1. So there's a downward force here called T1. And there's going to be a downward force here called T2. Many of you are like, well, it's the weight that's pulling, but it's not. The weight isn't attached to our pulley. The weight isn't pulling on it, the string is. The string is definitely affected by the weight. The more weight we have here, all else being equal, the more this string is going to pull. That's true, but it isn't the weight that's pulling on it, it's the string. If you were this pulley, if you curl yourself up into a little snail ball, and somebody wrapped a string around you, and then asked you if you could feel the pulling, you would be able to feel it if they pulled on the string, or if they hung something off of it, or if they attached it to a horse and the horse galloped away. If you don't know what's pulling on you, you don't know what's pulling on the string. All you know is the string is pulling on you, and that's what's happening here. The tension in this string pulls straight down at a 90-degree angle. The tension in this string pulls straight down at a 90-degree angle. Because these angles are 90 degrees and are a fixed location relative to the center of rotation, that means each one of these strings creates torque. And this is where I think you got to, right? This is where you left off, is recognizing that, oh hey, there's going to be torque here. The torque from this first string is going to be equal to the magnitude of that downward force times the distance to the center of rotation. That torque, all else being gone, would cause this wheel to accelerate in its positive direction. So that's a positive torque. Over here, we're going to have a torque that is proportional to the magnitude of this force and the distance to the center of rotation from where that string is attached. but that torque would cause the pulley to spin in its clockwise direction. So this torque is negative torque. So we have two torques, T1 and T2. T1 is in the positive direction, T2 is in the negative direction. And here's where I just want to take a quick time out and say two things. One is, this piece, I would think you might not have been able to figure out on your own, but ideally you would have gotten reasonably close. You would have recognized that there's going to be something going on here and here, that it's related to these forces. And then torque is the twisting force that happens when we pull on something with leverage relative to the center of rotation. And that's exactly what's going on here. We have one twisting force that is tending to cause it to accelerate counterclockwise, one twisting force tending to cause it to accelerate clockwise. And the combination of those two torques will determine how this wheel, how the pulley accelerates. The other thing that I want to bring up, and this is one that I think is more challenging, this would be way more difficult, I think, to figure out on your own, is what do you do about positives and negatives? Because these two forces are negative, right? And so that's negative, except this is negative of a negative, or is that just negative? And the answer is, we had a convention for dealing with forces. Forces are not negative. This is not a negative force, nor is this. Forces are always positive, always. There is tension, positive force, right here, pulling down on the side of the wheel. That same tension is pulling up on this mass. Neither one of those forces is negative, because there's no such thing as a negative force. Depending on your frame of reference, you can have forces in negative directions. We don't care about that yet. We will, but right now we don't. What we care about is the torque. This is going to be a positive torque. So we take the magnitude of this force and multiply it by the distance to the center of rotation. And because that torque is in the positive direction, we don't put a negative sign anywhere in here. Magnitude of this force times the distance to the center of rotation is going to give us a positive number, and that's what we want, because this torque is in the positive direction. Over here, we're going to take a magnitude, T2, times a distance, R2, and that is in the negative direction. This torque is in the negative direction, so we got to put a negative sign in front of it to indicate that. Forces aren't negative, torques aren't negative. If they're in the negative direction, we want to make sure that the overall sign is in the negative direction. And we'll come back to the business of, okay, well, how do we deal with like the up and down of the forces in just a second. All right, so far so good. So now we're going to get into, so this piece is something that I would have expected that you could have at least recognized, that the torque was going to be determined by the force and the distance to center of rotation. I wouldn't necessarily have expected you to come up with the correct signs here, but these are, in this case, with our conventions, the correct signs. Here's where it gets trickier. We've talked about this a bunch of times, the idea that if you have an object and it is being suspended from a string, what is the tension in the string? How much force is pulling up on this object? What? It's the weight, right? These two forces have to be equal. They're always equal. That's why when you hold an object like this, the elastic, see this elastic stretches out and then it just stays the same. It's the same amount of force, right? The elastic has to pull up with the same force as gravity. And even if I move this thing up or down, that won't change, right? Even if I move it fast, like if I move this really fast, you won't see this elastic get any shorter, will you? It's got to stay the same length, right? Look carefully. Tell me if it stays the same length. Did it stay the same length? No, it didn't. Yeah, that's not true, is it? And we ran into this before when we were dealing with the accelerating carts, and what I told you then was that this is something that no one ever truly masters. Our brains look at this situation and instantly think tension, weight, equal and opposite. But that isn't always true. It will be true if there's no acceleration, which means motionless. or constant velocity. But as soon as you have acceleration, these forces become unbalanced. One of them will be bigger than the other one. In particular, the sum of these forces will equal the object's mass times its acceleration. Now I'm leaving off negatives, so forget about, there's gonna be some algebra here that doesn't quite work out. But the tension force plus the weight of this object have to combine mathematically to equal its mass times acceleration. That means its tension force is gonna be related to the weight and the mass times the acceleration. We don't have our negatives here. Our negatives haven't been squared away. But this idea we've talked about before. It is super hard to remember because of the diagram.
What if we were to drop that same thing off like on the top of the school internet would free fall, the elastic would stay at the same distance the whole time? Right?
No, it wouldn't. If we were to drop it, then the elastic would get real smooth. There would be no tension at all. Yeah. If this object were in free fall, then mg would equal ma and tension would be 0. Yeah, and if it were to accelerate upward, I can't do this as well because I'm too short, but if we accelerate it upward, you'll see this elastic stretch out during the brief moment that I'm tall enough to give it an upward acceleration. You'll see the elastic spreads out. Did you see that? That's fine.
What if you were to just very slowly, constantly?
If you move with a constant velocity, then there's no acceleration. That means that, yeah, the tension and the weight are equal. So yeah, if you move with a constant velocity, you don't see a change in the elastic. But in this case, we know there's not a constant velocity. The mass on the right is going to accelerate up. The mass on the left is going to accelerate down. We have one more trick that we have to deal with. Okay, so this piece, you should have known. You should know this already. You're gonna forget. If you're in AP Physics, be prepared. They're gonna do this to you. They're gonna give you a scenario where you have an object being partially supported by a string. Maybe it'll be motionless. Maybe it'll be moving at a constant velocity. Maybe it'll be accelerating up or down. This is the key to the tension in that string. This is the key, is recognizing that it depends not just on the weight, but on the acceleration as well. And so now we have one last trick up our sleeve here, and this is the weirdest one because this one is kind of like, this doesn't make sense until you see how much easier it makes the math. So we have a counterclockwise acceleration here that's in the positive direction. It turns out that everything is easier if all three of these things are accelerating in their positive direction. The signs for all the work we're doing will be 1,000,000,000 times easier if everything is moving and accelerating in the positive direction. So what that means is we're going to make down positive for mass 1. We're going to make up positive for mass 2. And we can do that. There's no reason we can't do that. We just have to kind of keep track of it. So that means that for mass 1, the sum of the forces look like this. The sum of the forces are equal to its mass times its acceleration. Down is positive. Tension is in the negative direction. It's not a negative force. It's in the negative direction though. So this magnitude of force in the negative direction is negative T1. This magnitude of force in the positive direction is plus m1g. That's going to equal mass 1 times its acceleration. If I solve for T1 here, I get that T1 is equal to m1g minus m1a1. The tension is less than the weight, and that makes sense. There's a net downward force. This force is smaller than this one. Down is the net force, so we get a downward acceleration. With mass 2, it's effectively the same math, but we get a slightly different version of this relationship because we're going to say that up is our positive direction because it's going to accelerate up. So that means when I apply Newton's second law and I sum the forces, I have a tension force in the positive direction, I have a weight in the negative direction. And when I solve for tension here, I get that the tension is going to be equal to the weight plus mass times acceleration. The tension is greater than the weight, and that makes sense because it's accelerating upwards, so this force has to be bigger than this one. The accelerations are going to be positive because we know already that this thing is going to accelerate in the counterclockwise direction because I told you it would. If we didn't know what direction this was going to accelerate, all this math would still work. We just have to kind of consider that it might be that we have negative accelerations here, but we wouldn't, not in the case that we're looking at. Okay, we got one last issue here. So if we think about all the variables that we've got going on, we've got some torques, we've got some masses, we've got some accelerations, we've got some g's, we've got momentum inertia. And the thing about these accelerations is what we're trying to find is alpha. Right now, we've got a bunch of stuff, including the acceleration of mass 1, the acceleration of mass 2, and down the road, you'll see we also have the angular acceleration of the concentric pulley. Those three accelerations can be related to each other. And this is the last piece that I would hope that you would have seen, which is that this point right here on this string has to have the same acceleration as every point on the string, which will also be the same acceleration as m1, which means the tangential acceleration right here, I'm going to draw a box here just to clarify. The tangential acceleration of this point, which is alpha times r1, is going to be the same as the linear acceleration of mass 1. And the tangential acceleration of this point right here is going to be equal to the angular acceleration times r2, and it will be equal to the linear acceleration of this block on the right. What I would want you to see is the connection between the tangential acceleration here and the angular acceleration of the wheel, the tangential acceleration here and the angular acceleration of the wheel. Those are our move back and forth from linear to angular realm variables, okay? We could do that with angular displacement, we can do it with linear displacement, we can do it with angular and linear velocities, and we can do it with angular and tangential accelerations. We can switch back and forth between thinking about how fast this thing is accelerating in meters per second squared and how fast it's accelerating in radians per second squared if we know how far it is from the center of rotation, which we do. And that's the last piece of the puzzle before we shift into just kind of using algebra. So if we just do a substitution here, knowing that this tangential acceleration is the same as the acceleration of this block, we get that the tension here is going to be equal to m1g minus m1 alpha r1. It's related to the tangential acceleration of this point, which is related to the angular acceleration of the wheel and the distance of that point to the center of the wheel. And this tension right here is going to be similar in that it's related to the angular acceleration of the wheel and the distance from this point to the center of rotation. I would not have expected you to get this or this, but I would have hoped that you would have seen, oh, well, this point right here should be accelerating with a tangential acceleration equal to alpha times r1. That is from those that set of formulas that I gave you last week that relate linear and angular quantities. Okay, now we can put it all together. What we're trying to find is the overall angular acceleration of the wheel. Newton's second law for rotating objects says that the sum of torques on an object is going to be equal to I the angular mass of the object, which we know, times alpha, which is what we're trying to find. Sum of torques was the hard part, but we now know what the tension is at each of those points, and we know the torque in terms of the tension and the distance to the center of rotation. So that means that our sum of torques is going to be T1 times R1 minus T2 times R2. The positive torque on the right side of the wheel minus the torque on the left side of the wheel should equal this object's moment of inertia times its angular acceleration. Since this is my tension on the left side of the wheel, this is my tension on the right side of the wheel, I can substitute and I get M1G minus M1 alpha R1 all times R1 minus M2G plus M2 alpha R2 times R2 equals I times alpha. This only has our unknown, alpha, and all the things that we did know. We know the masses, we know their distance to the center of rotation, and I told you the moment of inertia. Small, 10 to the negative 3, somewhere between 10 to the negative 3 and 10 to the negative 4. The rest is just algebra, and here's what the algebra looks like. If I distribute here, I get M1G R1 minus M1 alpha R1 squared. Distribute the negative sign in the R2, I get, minus M2G R2 minus M2 alpha R2 squared. All of that equals moment of inertia times alpha. And now if I'm gonna flip my equation, so I'm gonna make this the left-hand side. I'm gonna add M1 alpha R1 squared and M2 alpha R2 squared, and I get I alpha plus M1 alpha R1 squared plus M2 alpha R2 squared, all equals M1 G R1 minus M2 G R2. And this algebra is not, I mean, ideally you'd be able to do this, but realistically, this is where you might start making a lot of mistakes. I sure did. The first time I did this, I did this 5 times with this brilliant student teacher, and we got a different equation every single time. Everything was the same except the minus signs. Like every time we did it, we had different negatives. It took a while for us to come up with, oh, up is positive on the left, down is positive on the right, counterclockwise is positive for the rotating object. Make sure that we follow our conventions for Newton's second law for linear objects, that all of our forces, variables are always representing positive numbers, and everything fell into place from there. But getting to here the very first time was not easy. If I factor out alpha here and divide by whatever's left, what I get is alpha is going to be equal to M1 GR1 minus M2 GR2, all divided by I plus M1 R1 squared plus M2 R2 squared, and this is how you make your prediction. If you wanted to find alpha, you could effectively use this same equation and just hang some masses on there and see what happens. But once you know moment of inertia, you can use that to predict future alphas. So here's what I want you to do. In the next 7 minutes, I want you to first do the best. I mean, honestly, I mean this sincerely. If you were to ask me to do this calculation right now, I could get the right answer, but I'd have to go pretty slow, just to make sure that I didn't mess up any of the math. If you gave me 7 minutes, I'm not entirely confident that I'd get the right answer, but I want you to try. It's not that big of a deal if you mess up on the arithmetic. I also want you to take a picture of the work you did, combine it with the work that I just showed you, combine it with however far you can get here toward a prediction, turn it all in. And then, if we were living in an alternate universe where we had lots more time, I would have done a lot less of this, you would have done a lot more of this. Normally what I say to you is, it's not good enough for you to be able to just understand what I did. In this case, not only is that perfectly acceptable, it's also okay if you didn't understand all of this. The stuff that I want you to get, the stuff that I really wanted you to understand was, number one, don't forget about this. Don't forget that tension and weight aren't equal always in this situation. Number two, we're gonna have downward acceleration of one mass, upward acceleration of the other. Those accelerations are not gonna be the same because the pulleys aren't the same size. Number three, the torque here and here are what will determine the overall acceleration of the concentric pulley. Number four, we can relate the angular acceleration of this point and the angular acceleration of this point to the tangential accelerations in these locations. The rest is a bunch of algebra and a bunch of logic and a bunch of like conventions that I don't expect you to really be able to do. You could down the road, but you didn't spend enough time on it. So come up with a prediction, turn in everything you've got, and then tomorrow we're gonna move on to some other stuff involving rotation. We've got 2 more things to look at with rotation before spring break, and we're gonna knock it out.
I'm not really able to make a prediction based on my own data because I was off in state